Alrighty. So we have the exam. Let me just start by taking some of my broken chalk that I just dropped and putting up topics here. So there's draw derivatives and antiderivatives. And there's my phone. Let's see. Okay. It's probably somebody trying to get me to vote for somebody. Okay, so fundamental and second fundamental, FTC, so fundamental theorem of calculus. Okay, so we have those. We looked at Riemann sums. We looked at integrals and antiderivatives, and of course definite, integrals, antiderivatives, and I don't have written down here derivatives, but also derivatives, and derivatives of e to the x, natural log of x. Now, and we didn't have a bunch of homework problems over them and so forth, but what I pointed out was, hey, if you can go look up the antiderivative or the derivative, we know what to do now, and so I'm going to toss in everything else. Okay, so there were the all the trig functions, the inverse trig functions, the hyperbolic trig functions, all that stuff. As long as we can find an antiderivative for it, if we can look that up, then we can do all the stuff we've been doing. Oh, I see. I had that on the derivatives part. I had on a different line. Okay, and then average value and differential equations. Now, the differential equations was really just antiderivatives where you were given some information to find C. So C was no longer an arbitrary constant. We had to actually figure it out because we were told, oh, we want a specific antiderivative. That's all the stuff they did with differential equations there. And then we had to do a bunch of things with area. Right. That's kind of how the whole idea of integration was introduced and so forth. Now, I will tell you that I left something off this list because I didn't think about it as I was writing up the exam, and the exam's plenty long enough as it is. I didn't need to add that. But derivatives of inverse functions, right? Because that's how we got the exponential function was inverse function of natural logarithm. And so they did some things with derivatives of inverse functions in 5.3. I didn't put that on the exam. Okay, so I thought that I could put this, these are the things, the topics that we've hit. What kind of questions do you have? Questions over any homework problems? Any of these topics, you look at them and you go, huh, I don't think we ever did that. You know, that's always a possibility, right? You look at it and you go, huh, I don't remember that. Any questions on anything? And I've tried catching up on some videos from, just doing problems from the text. I made a couple more. Well, actually, I put quite a few on yesterday. But I started putting some on, I started making some from 5.4 today, and haven't put any of them up. I only have a couple from that. Not that this really slowed me down that much. I mean, there are plenty of other things to slow me down, but so I got this nice new tablet, and that I was kind of getting used to that. And well, now I'm going to get another new tablet on Saturday, because this thing kept having a black screen of death as I would do. I'd be working on it, and it'd just go, and display was gone. And so I checked with Samsung, and they after they told me to do things that I'd already done, they said, "Oh, yeah, it's broken. Something's wrong with it." So they suggested I send it in and all that, but I could still. It's new enough. I've only had it 2 weeks, so I just sent for a replacement, and hopefully we'll have that this weekend. And again, not that, I've got my other tablet that I can do things on. So, okay. So, have I stalled long enough? Do you have questions? Anything? Nothing? So, now normally I would, if we were meeting 5 days a week, I'd just tell you I'll leave at this point. But I don't feel comfortable doing that with only meeting 2 days a week. And or I would just start on with new stuff. But actually, probably our new stuff that we'll do, we won't really do very much at all out of the textbook, I don't think, just because we're behind on projects and all that. So I think we'll use the next session to try to do some projects and go over some of the things we've already done with one small project over the next topic, which is differential equations. But okay. Well, so let me just ask you. So you're comfortable if I, draw something like that and tell you, oh, okay, that's f of x, and then I tell you further that uppercase f of x, f prime of x is little f of x, and I'd like you to draw uppercase f of x. That's a piece of cake? What? No. Right? What do you have to look for? What would be good things to look for? Right? So this is the derivative. Okay? What is it about a derivative, or a function, either way? You look at a function, what do you notice about its derivative? And therefore, if you knew something about its derivative, you could go back with the function. Right? What's that? The points of intersection? Yeah. So I can look here, right there, and right there, those, and let's just add some numbers in there. So there's -1, say that's 2 and that's 4. Then I know that the critical numbers of f of x, uppercase f of x, are -1, 2, and 4. And since everything's really nice here, nice and smooth, then I also know that those are relative extrema at those x values. Okay? So I know that. Now, so critical numbers give me intervals. And so what can I say about the interval from -infinity to -1? What can I say about that interval and my function uppercase f of x? Well, what's little f of x on that interval? Does it look like? What sign does it have? Negative. Okay, so if the derivative is negative, what does that mean about the function itself? It's decreasing. So on here, I know it's decreasing. And then I can go between -1 and 2. Oh, well, it's positive there, right? So it's increasing. And similarly, between 2 and 4, it's negative again, so it's decreasing. And between 4 and positive infinity, it looks to be increasing again. Okay, so we have that information, and that's really all the information we have. Now, we could toss something else in, right? We could, much like a differential equation, we could say, oh, and by the way, f at 2 is 6, or something like that. But we'll worry about that in a minute and just kind of point out what we could do. So here's my graph, and so at this point what I realize is, okay, it's decreasing, so f is decreasing, big F, then it's increasing, and then it's decreasing, and then it's increasing again. And so I could draw that function, and if I wanted to, I mean, there's nothing to keep me from doing it. I guess I could do that and call that uppercase f of x. Now, I don't have to, it's not wrong if I don't do that. I mean, it's actually more likely, when all's said and done, to be wrong if I do that. If we were trying to be really, really careful about it. But now, I'm just trying to get an idea of what it looks like. But if I now, I've come up with that, and then I toss in that, oh, by the way, f of 0 is -2. Okay, all is not lost. I can fix that. All I have to do is keep that same sense. So here's the -1, there's 2, there's 4. And remember, I needed something that came down and had a minimum here at -1. Well, if I'm going to have f of 0 be -2, so maybe there's -2, I just need this thing right in here to be a bit lower, right? Because it's got to go through 0, -2, right? That part just needs to be down here. Well, there's nothing stopping me from just, doing that. And if I wanted, I could leave kind of everything else the same and do something like that. And there's my f of x. And I've made it happen. Okay. Now, I suppose, you could also estimate where this function is concave up and concave down. So if I'm looking at the derivative, so let me get rid of f, the big F here, for a moment and look back at this. So this is the derivative of the function. So if I want to know the concavity of the original function, big F of x, what do I need to look for here? What do you look for in the derivative for the change in concavity here?
Points where it's parallel to the, or where x is, or no, y is equal to 0?
Not y is equal to 0, but its derivative. So here and there are inflection points. Now, you got to be careful. If I just leave that there, somebody just walking in that knows their stuff would say, that's not an inflection point, that's a relative maximum. Right? So it's inflection points of big F of x. Okay, because remember that as you're looking at f, right, it's where, not where the derivative changes sign, right? Because here, the inflection point, I don't know, it's maybe there or something like that. So the inflection point, it's increasing that whole way. So the derivative doesn't change sign. So little f of x doesn't go from like positive to negative or negative to positive. But it's the steepest right there. That's where the derivative has either a maximum or a minimum. Okay, so it's the steepest right there, it's the steepest right in there, but it's a negative number. And if you look here, right, there are two relative maxima here, and there are 2 points of inflection there. Okay, and they're relatively in the same place, right? Between 0 and 2, or between -1 and 2, and between 2 and 4. Okay, so, really, when it comes down to it, sort of looking at the picture to do these things, what it's really stressing you to do is know your definitions of what these things are, and to have some kind of internalized intuition about what they are. Okay, so, inflection points happen at that steepest spot. Okay, or let's see, and again, steepest on a negative. So, so in that case, we're going to look for relative maxes and mins on the derivative. Now, though, right, this derivative function, it could have had it could have gone like this, where the from all this, the function was increasing and so forth. So I mentioned the steepest for an inflection point, but remember that I could have something that looks like that, and there's my inflection point, and that's the least steep spot as it's going up. Okay, so that would be something more like that. Okay, because the slope, this slope function here, little f of x, is positive, so I had to be increasing. Okay, but it's at a minimum, so it was the flattest there. So it's either the steepest or the flattest, but it's where the concavity changes. Okay, so, you know, alrighty. So that's the idea with drawing the, you know, drawing antiderivatives and derivatives, is you're thinking about the things that you notice on a given function, or its derivative, or its second derivative, that kind of thing, and thinking about what those are, and then what that means in the graphical or visual arena. Okay. So now do you have questions? Anything come to mind? No? Okay. Okay, so fundamental theorem of calculus, I think that is, you know, if you've done your homework and done antiderivatives and then definite integrals, well, that's really the fundamental theorem of calculus, is just that definite integral. But now the second fundamental theorem of calculus, right, so second FTC is that whole idea of taking the derivative of a function defined by an integral. So that derivative, oops, that should be like an S or something. You know, that derivative by the second fundamental theorem of calculus is just f of x. Okay, so, you know, there are lots of ways to attack this sort of idea, right? So, for instance, you know, think about the sort of questions that you just get asked about functions, but then what if the function was given this way? You know, so you could be asked things like, you know, maximize. And suppose I gave you a function, now I'm going to call it f of x this way, is the integral from, say, 0 to, I don't know if I'll get a maximum or a minimum now that I think about it, but x of, well, we'll just make it pretty simple. Let's see. So, yeah. So if I do something like 2 minus s ds. Okay, and or instead of maybe saying maximize, I could ask you, you know, what are the critical numbers? Right? That's probably the more fundamental question here. What are the critical numbers? Right? So maybe critical numbers. And then we can worry about whether maximum or minimum or something like that. So if you look at, oh, that should be an S. So if I have a function defined this way and I say, what are its critical numbers? What do you do? Well, if I just gave you any function and I said, what are its critical numbers? What would you do? We sort of just did it back here. It was graphical.
Equal the function to 0.
Which function? Right? If I tell you I have a function and I want its critical numbers, what needs to be equal to 0? The derivative of the function, right? Okay. So to find those critical numbers, I need that. But remember, the derivative is just this, so we have 2 minus x has to be 0, x equals 2. Pretty simple. See, so these are the kinds of things that from a calculation point of view, they really don't take much. But you actually have to remember what these things mean. Okay? And so, that's an idea with the critical numbers. And now, I could ask, right, is that, okay, so there's a critical number. The function, I'm sure, is defined there, because this is a nice antiderivative definite integral thing. So there's a critical number, x equals 2. Am I going to find a minimum or a maximum? Well, that kind of comes down to this function, 2 minus x, right? What's it doing? Well, 2 minus x has a negative slope and a y-intercept of 2, and so it does that to hit x equals 2. Oh, okay. So here, f prime is greater than 0. Here, f prime is less than 0. At x equal 2, I should find a maximum. Okay, a relative maximum because the function's increasing and then it's decreasing. Right? So this is the derivative is positive and then negative. The function is increasing and then decreasing. And I could tell you the y value. Oh, well now, okay, f of 2, well now I actually have to do some calculation. 2s ds. And so I would have to do that antiderivative and the integral then. So this is, this is 2s minus s squared over 2 from 0 to 2. And I get what? 4 minus 2. A lot of 2's in this. I just made it up. A lot of 2's. So in that way, it's a horrible example. I don't like examples that keep the same number coming up in all different places. It's hard to tell what's going on. But nonetheless, we've got our relative max is at x equals 2 with a y value of 2. Okay? So, that's a way we use the fundamental theorem of calculus. The other, we can take derivatives, right? So, second fundamental theorem of calculus. So, we have that. But now, what happens if I make that a 2x? Okay, that's some of the stuff we did in the text. What happens if that's a 2x? What's the derivative now? Okay, and if you're not sure, well, start with this. The integral from a to 2x of f of s ds, well, I have to define what uppercase f is. I mean, if I just write an uppercase f, it does not necessarily mean it's an antiderivative, but this would be, according to the first fundamental theorem, that's that. As long as, so that's given that f prime of x is our little f of x. Right? Then that's exactly what the fundamental theorem of calculus says. Okay, now, if I want to take the derivative of this thing, Well, what's the derivative of big F? Little f. Okay, but it's, right, I've got a chain rule going, but it'd just be little f of 2x, but then times the derivative of 2x with respect to x, and then minus, but f of a is a constant, right? We're assuming a is a constant, so that's just a constant. So we have 0, and so here I get 2f of 2x using the chain rule. So we can take derivatives, all sorts of derivatives, even if stuff is really weird up there. And then, now you could also run into one slightly different sort of thing. What if you had defined your function going from x to a like that? Now what happens when you take a derivative? And really the key here again is just, well, by theorems and definitions and so forth that we've been given, well, okay, that looks hard. I don't know what to do with that. But I know that I can simply, instead of writing that, I can write minus the integral from a to x of f of s ds, and now I know the answer. Okay? Because I know, take away the negative, well, the negative just comes outside, so I know the answer. Right? I can just write this as minus f of s. And it really didn't take much, but I had to know those relationships. Okay, so a number of items in this exam are about actually knowing what the vocabulary means. They aren't hard in the sense of, as long as you know this is true, this is not hard. You just have to know it's true. Well, how would you know that? Where is it hiding? Oh, well, in the reading and in the problems and so forth. They put it right out there. It's there. And so it's a matter of really knowing your vocabulary. And that's where I am a bit different. I could just leave it at that. But I am a bit different than many math teachers, certainly ones that you had probably pre-college and so forth, many of them, not all. But I guess because I teach upper level math courses, I realize how important it is to know your definitions and to know your theorems in those relationships. And usually a lot of problems become so much easier if you just know those. Well, kind of in the past, what it was really calculus was just taught as applied algebra. And in that way, that was fine, really, at the time. For one, we didn't have all the technology to do algebra for us. And the other was we knew algebra. We were drilled on it coming up through school, people my age, and best I can tell is, at this point, your generation, the schools really aren't asking you to know that algebra. Not really well. Not like they ask us to know it. And, okay, that's fine. It just means I don't teach this course as an applied algebra course. Okay, so I want you to start looking at the real mathematics that's going on And it's things like these relationships that we're given. And algebra is definitely real mathematics, but honestly, and I'm not saying this to like make you all feel bad or something. It's just the state of education and what's being emphasized or not emphasized and so on in education. It's kind of hard to do a really heavy applied algebra course with people who don't know their algebra that well. And so it makes it easy to make that choice. But yeah, what often happens in upper level math courses is if you've gotten nothing but sort of the applied algebra approach to calculus, you hit an upper level course and all of a sudden they're really, really focusing on definitions and theorems, and you feel very lost. And that was me. Okay, I hit those courses and it was like, I used to like math. It was fun at one time, right? And so, but I figured it out. I realized what they were doing, and it actually then makes the rest of math way easier. So we just really ought to push that more in the lower grades and all that. Okay, so area stuff, right? That's on there. Now area, here's a case where actually on the exam I tell you, once you set up integrals for the area, you knock yourself out, use technology, just tell me that, oh, I use Sage or I use Desmos or something like that to evaluate the integral. Because at that point, it's sort of boring, right? I set up the integral, I know what I'm doing, I modeled the situation, now I just want an answer. Okay, yeah, that's what technology's for. So, area, we were originally given problems like, y equals, say, negative x squared plus 1, something like that. And we'd like to find the area bounded by this. So area bounded by that and the x-axis. Okay, so if I want to know that, I need to probably plot it. And, I can go to something like Desmos. Desmos is great, right? Just plot it there very quickly. Now this, I chose something I know what it does. It's just a parabola. There's actually the relative maximum up here at 1. So it opens like that. I would like that area, I guess, because it's bounded by that and the x-axis. Now, well, this area down here is also bounded by that in the x-axis, but that's silly. Right? That's an infinite amount of area. I can just tell you that looking at it, and so not that interesting. Okay, so I need to know that is at -1 and that's at 1. I need to know the bounds that I'm going to do my integration over, and then I can set up my integral -1 to 1. Of either minus x squared plus 1 or 1 minus x squared dx like that. And there you go. Now I either do my power rules and figure out what that is, or I just toss it into some sort of technology and say, hey, what's the answer? Okay, and then I can kind of check it and go, oh yeah, So if I did this and I get a negative number, something seems very wrong with that, because all these heights, and remember that's what an integral is really doing, It's not really finding area. It's adding up all those heights over that interval. And, well, all those heights are positive. I should get a positive number out of it. Okay, now, what happens, though, if you just change it slightly, right? And so suppose you said area bounded by y equal 1 minus x squared. Okay, so I have that. And now, I don't know, let's use y equal x. Okay, as I look at that picture, I get something that looks like that. And so, once again, the only region that makes sense in that is that region. Now, in this case, there are various ways to do this, but what's very important is I need to find that point and that point. Now, again, something like that, I am fine with using, a graphing utility like Desmos to either, zoom in on those points. I mean, that's fine. Or set up the equation that you need to solve, and then use something like Desmos to figure out what that is. So here, what do I have? Well, I have that the function y equal x and the function y equal 1 minus x squared have to be the same. And so that says I need 1 minus x squared to equal x. And so I could write that as x squared plus x minus 1 equals 0. And I could find the x values that way. Again, I could graph it and look at where it's 0, that function's 0. I could use the quadratic formula on it and get some numbers, right? So, I'll do that. So in this case, x is equal to the minus b, so negative 1, plus or minus the square root of b squared, so 1, minus 4ac, well, those are both 1, so that's just plus 4 because of that negative. And then all over 2a, so I just get 2. And so x is negative 1 at plus or minus the square root of 5 all over 2. Whatever the heck that is. Right? So there are my limits of integration. I know that I want to go from there to there. And so this is the square root of 5 minus 1 over 2. And this is negative square root of 5 minus 1 over 2. And now, again, there are various ways you could do this. The thing to really remember is all you're doing with an integral is you're adding up heights. And so I could tell you the height of each of those spots just by taking the value of this curve minus the value of that curve. That's probably the most straightforward way to come up with this, right? Is that I would just set up the integral from minus square root of 5 minus 1 over 2 to square root of 5 minus 1 over 2, and I would take the top function there, the 1 minus x squared, and I would subtract off the bottom function, and I would add all those heights up. And that's all that an integral does. It just adds up the heights along the x-axis. And it doesn't matter how you get those heights. Now, if I did x minus this one, well, I would get a value, but it would be the negative of the area. Because if I took this one minus that one, I would get negative numbers that I would add up. Okay, but if you don't really like that idea, right? Well, you can fill in other things, right? That's -1 and so forth. And so I could find the areas of lots of different pieces here. So drawing this again here, I could find the area of that. Right? I know that goes from -1 to 0, and I could just find that area all by itself. And that is just, that's that integral. It's bounding with the x-axis and so forth. So we know how to do that. Then, now notice what happens here is, see, I could find that, which if I call that area A, that area is the definite integral from -1 to 0 of 1 minus x squared dx. Okay, so I could find that area. Similarly, now this is where it can get kind of tough, because now if I drew a straight line down like that, I could find that area, and I could find that area using geometry. I don't even need an integral. Okay? So I could find that area. Then here, I could find this whole area here. That's easy enough. Again, it's an integral a lot like this one. Actually, right? It's exactly the same amount because of symmetry. So I could find that area. And so this, if I called that whole thing area B, then B is actually equal to that as well. Or I could do it from 0 to 1. Okay, but again, the areas, they're symmetrical. I should get the same answer. Then I could subtract off that triangle. And again, I don't need an integral to do that. I could find that just using geometry. So, I could subtract off that. Now notice in here, this is very simple to see, I think. Oh wait, that's not a triangle, is it? Okay, I'd have to stop it there. And so what happens is I get these two little pieces that I need to do. Okay? This piece, not a problem. Again, if you blow that up, you're trying to find that area. Okay, so you could do that. Now, as you see, this gets very, very complicated. I mean, each piece is just an easy integral to do. But it gets complicated slicing this thing up. Okay, now why is it so complicated? Well, because if we don't understand that all this integral sign is saying is to take a bunch of heights that correspond to all these different x values, and all we're doing is adding up all those heights. Right? If I get that, then to do this problem this way is really easy. Well, a lot easier than trying to keep track of all this stuff. Okay, and again, remember how we define integrals and area and so forth, is that if I take a picture like this, right, all we do is make rectangles. So here are my rectangles. Now how do I find the height of each rectangle? I just take the top curve minus the bottom curve. And so with the Riemann sums, I'm just adding up all those rectangles, making them skinnier and skinnier as I go. But you see, it doesn't matter if that rectangle is sitting down here, if I take its height, or if it's sitting up above the x-axis. Doesn't matter. I just want the rectangles. And so you see, if we really get what this sign here means, this funny looking S, it's really not bad. Okay? Because all I have to do is know where to start, where to finish, and think about those rectangles I'm adding up that are getting skinnier and skinnier. And it just becomes, the one function minus the other, and I can get an answer quite easily that way. Okie doke. Well, so we are out of time. I'll make that available. It's due Monday. If anybody has any issues or of some kind or other, just let me know, as opposed to trying to just somehow think that you can take care of them. And if you have a problem, let me know what it is so no one panics about the exam, okay? All right, I will see you on Monday.